In the century that followed, scientists would explore further than ever before. German scientist Alfred Wegener was at the vanguard. Rare footage of his final expedition to the icy heart of Greenland in 1930 still speaks of a time when much was to be learned in the far reaches of the Earth. Science here was a struggle against the deadly powers of nature. These rigorous expeditions would enlarge Wegener's curiosity about the Earth. Wegener conducted many meteorological experiments, but he was curious about more than weather. He was puzzled by glacial deposits in the tropics, by identical fossils on continents thousands of miles apart, by mountain ranges with the exact same geology, but separated by vast oceans. His curiosity drove him to seek an imaginative solution to these scientific puzzles. Like Greenland's sea ice, perhaps continents could also split and move apart. Wegener's bold leap was to reconstruct a world where the continents fit together. His sketches connected broken mountain chains and solved other unanswered problems. This single giant continent is called Pangaea, all lands. Though based on careful scientific reasoning, Wegener's ideas were dismissed as fantasy by scientists of his day. No force could possibly plow whole continents through the bedrock of the ocean bottom. Wegener died in Greenland, lost in the far reaches of a frozen wilderness. But his vision of moving continents would haunt the scientific world until new discoveries at the bottom of the sea revived his challenging ideas. In mid-century, global research, highlighted by the International Geophysical Year of 1957-58, provided new ways of looking at the Earth as a planet. Spurred by this global view, scientists would explore and map the ocean floor and collect data that would lead to the discovery of an Earth far more dynamic than ever envisioned. In the mid-Atlantic, scientists would discover a mountain range that mirrored the coastlines with summits reaching 10,000 feet above the ocean floor. The mountains wind 46,000 miles around the globe like the seam on a giant baseball. Split by a central rift valley and rocked by countless earthquakes, no scientific theory could account for these curious phenomena. For centuries, scientists thought the ocean floor was part of the original crust of the Earth, frozen in time when the planet cooled from a molten ball. But dredging brought up relatively young rocks and newly created volcanic lava. Surprisingly, no rocks were older than 150 million years. Sediment cores were plunged to the ocean bottom. Scientists expected the cores to read like an encyclopedia of the past, but billions of years were missing. Some 95% of Earth history was gone. Where did that history go? Why was the ocean floor so very young? In 1960, Princeton professor Harry Hess proposed an idea later called seafloor spreading. He supposed that molten rock rising in the deep valleys of these undersea mountains formed new seafloor and spread to each side as more new rock came from below. If so, an entire ocean floor could be created in 1 to 200 million years, a mere 5% of Earth's history. But lacking hard evidence, Hess called his idea geopoetry. Ironically, supporting evidence for seafloor spreading would be found on land, the site of an ancient volcanic eruption. Here in the Owens Valley of California, scientists probing one mystery would serendipitously provide a way to measure the growth of the ocean floors. When lava cools, it acts like a compass, freezing in the direction of magnetic north. But in several locations around the world, frozen compasses were discovered that pointed south. What did it mean? Do rocks somehow reverse their magnetism? Or more fantastically, can the Earth's magnetic field change direction? Since 1956, Alan Cox of Stanford University and Brent Dalrymple of the U.S. Geological Survey have explored this magnetic reversal mystery.
Our idea was to collect rock samples from all over the world. We would look at their mineral content, the direction in which they were magnetized, and their ages, and compare these. If rocks were magnetized to the south because they contain peculiar minerals, then all rocks magnetized to the south contain those peculiar minerals. On the other hand, if the wild theory that the magnetic field had flipped was correct, we'd find that rocks from all over the world recorded this flip at exactly the same time.
Yeah, I'll see what I can find here.
For accurate testing, the scientists must find lava undisturbed since the eruption.
The reversal hypothesis was an exciting one to me because it involved the entire Earth. It was a global phenomenon. And somehow I thought it was just marvelous that the Earth's magnetic field might have reversed itself. There was no proof of that. It was just a hunch.
A diamond drill is used to obtain cores of lava. Back in the laboratory, they are dated and carefully measured to determine whether they are magnetized to the north or south.
Good, thanks, Brent. I'll shoot that.
Before the core is removed, Cox takes a careful note of its orientation by using a compass to sight on a known landmark in the nearby Sierra Nevada mountains.
Azimuth.
Such precision is necessary to later accurately determine the lava's magnetic direction.
Y-axis is 281. This looks like a pretty good place to set up the footscape, Brent.
The frozen lava compasses here at Big Pine, California, reveal that the Earth's magnetic field did actually flip to the south almost 1 million years ago. What causes the magnetic field generated in the Earth's fluid dynamic core to reverse is yet another mystery. In the years following, the scientists from California and their colleagues would drill and date hundreds of lava samples from around the globe. They would find that rocks of the same age, whether from Alaska or Africa, simultaneously record the same magnetic orientation. This led to the construction of a time scale of magnetic reversals that plotted these flips. By 1966, Cox's group would confirm 9 north-south flips in some 4 million years. The discovery was like finding the Rosetta Stone. By cracking its hieroglyphic code, archaeologists unlocked thousands of years of Egyptian history and culture. But the geologists who helped solve the mystery of magnetic reversals would not be aware that their reversal code would also unlock a rich and dynamic Earth history. For a decade, research vessels had been towing magnetometers across the oceans. Here, over the mid-Atlantic ridge, the readings revealed strange and mysterious magnetic patterns. But no one knew what they meant. The key to deciphering these curious patterns would come from another team of scientists at England's historic Cambridge University.
People often assume that, well, we sort of had the idea in the bath or while shaving. Well, not collectively, but one of us had the idea in the bath or while shaving.
Frederick Vine, a young student, would team with Drummond Matthews to analyze a detailed magnetic survey Matthews made in the Indian Ocean.
Made in, what, 62?
Which I brought back from sea in 62, yes.
Which you brought back, yeah, just a few months after I started as a graduate student, and basically gave me the job of interpreting that.
Most thought the pattern was due to magnetic and non-magnetic bands of rock on the sea floor, but Vine and Matthews studied the data carefully and reached their own startling conclusion. Could the stripes of the pattern be a record, frozen into new ocean crust at times when the Earth's magnetic field was pointing alternately to the south, then to the north? At mid-ocean ridges, hot rock surges upward, cools, and is slowly carried away as if riding a giant conveyor belt. Vine and Matthews theorize that newly created seafloor, like volcanoes on land, records the direction of the prevailing magnetic field and leaves a matching pattern on each side of the ridge. The remarkable match of the magnetic patterns on the seafloor, stripe for stripe, with the magnetic timescale developed on land, establish the concept of seafloor spreading and also the rate at which the plates are moving apart. If Cox and Dalrymple had discovered the geologic Rosetta Stone, Vine and Matthews learned how to read it.
Yeah, that was really the point. That was really the point.
1968, a specially equipped research vessel, the Glomar Challenger, is dispatched to the South Atlantic. It drills sample cores on either side of the mid-Atlantic ridge. Analysis of rock and marine fossils brought to the surface shows that the seafloor grows progressively older the farther it is away from the ridge. Glomar's drilling would provide the first direct confirmation of seafloor spreading, nearly an inch a year. Geopoetry had seemingly become geofact. 400 miles southwest of the Azores, scientists prepare for an extraordinary adventure. The French submersibles, Sienna and Archimede, with America's Alvin, will give scientists a first-hand look at a site of seafloor spreading. Dubbed Project Famous, the expedition into the deep began 4 years after man landed on the moon. Alvin sinks for 2 miles into a rift valley the size of the Grand Canyon. The scientists film seafloor cracks, evidence that the plates are pulling apart. Distinctive formations called pillows demonstrate that volcanic eruptions from below create new seafloor, similar to this pillow lava forming off the coast of Hawaii. The fires of creation burn under the sea. As this new lava and the rocks beneath it cool, they thicken to some 60 miles, forming the outer shell of the globe, called the lithosphere,